Good morning and welcome to this postgraduate video course on advanced hydrology. In the last few lectures, we looked at the chapter on unit hydrograph, all right. And in the just concluded class yesterday, we looked at the methods of determination of a unit hydrograph of a different duration than the one which is given to us, all right. For that, we looked at two methods. First one was what is called the method of superposition, in which the desired duration is the integer multiple of the given duration. The second method involved the use of S curve, and then we also used or looked at two different examples, numerical examples of these two methods. So, with that we will move on, and today we are going to start a new topic or a new module in this course, which is on stochastic hydrology. In this module, we will basically look at we will study or we will look at two chapters which are given in the Venti-Chau's book, all right. One is the chapter 11, which is on hydrologic statistics, and the next is the chapter 12. So, what we will do is we will get started with the chapter 11 today. From your Venti-Chau's book, and the title is Hydrologic Statistic. Okay. If I ask you what is going to be the rainfall tomorrow, what will be your answer? Well, you can say that the rainfall tomorrow may be 1.2 centimeters or 0.2 centimeters or few millimeters, or you can say that there may not be any rain tomorrow. But can you say that, can you make that statement with 100% confidence? No, we can never make any such statement about hydrologic variables with 100% confidence or 100% probability, all right. Why? Because most of the hydrologic variables are uncertain in nature, all right. There are lots of sources of error while we are analyzing, we are measuring the data, hydrologic data that is. That is why we need to consider the uncertainty, or we need to incorporate the uncertainty into our analysis, all right. So, what we are going to do in this chapter is we will look at some of the methods which are used to analyze or incorporate this uncertainty into our analysis, and how we can fit a probability distribution, how we can use the laws of probability and statistics to make judicious decision under uncertainty, all right. So, if we get started, there are many sources of uncertainty, but we will not look at all of them, just mention a few. Okay. There may be some instrumental limitations. All right, there is some instrumental errors may be involved while measuring the values of rainfall and flow, etc. Another is the measurement error themselves. All right. First one was the errors involved with the instrument, all right, and the second one is the measurement error, that is different people may read a different reading depending upon different times, all right, or subjectivity may be involved with that. Then we are doing the design, hydrologic design with historical records or historical data which may be erroneous, all right. So, the design is based on data which may contain error or uncertainty. So, our design has to be reliable, all right. There may be errors in your analysis due to system complexity. What do we mean by that? Our system may be extremely complex, but we may be substituting that or assuming a simpler approach, all right. So, that may be a source of error in your analysis. And then as I said, I am not going to list the remaining ones, many others, all right. Whatever be the reason of the sources of errors or uncertainty in our data, hydrological variables, all right, our objective is what? Our objective is to somehow incorporate this uncertainty in the hydrological process which we are modeling or representing. All right. So, what are the objectives? The first one, as I said, is, let me look at that. The objectives of stochastic analysis. There are mainly two objectives, and the first one is the probabilistic representation of hydrologic process. All right. For example, rainfall is a hydrologic process. All right. It is not a deterministic system. All right. There are lots of complexity, there may be errors in the data and so on. All right. So, what we do is we try to represent this process or any hydrological process using a probabilistic approach. When we say probabilistic approach or probabilistic representation of your system, what do we mean by that? As I just said at the beginning of this lecture today, that what will be the rainfall tomorrow? Okay? The answer cannot be 2.3 centimeters with 100% accuracy. What we may be able to say is that there is a 50% chance that the rainfall tomorrow will be less than or more than certain number, or you can say that there is a 60% chance that it will rain tomorrow, or there is a 90% chance that it will not rain tomorrow. So, you can make these kind of statements in which you are associating certain probability, all right, some factor between 0 and 1 or 0 to 100%. All right. So, this is called the probabilistic representation of your hydrological process. Okay. So, this is one of the objectives, and there are various ways of doing that. We cannot just put a number to the rainfall tomorrow. It has to be properly analyzed, it has to be properly deduced using the laws of probability and the historical data. Okay. So, we will come to that later in this chapter. What is the second objective? What is the purpose of carrying out this hydrological analysis of your variables under uncertainty? Well, all this analysis is going to lead us to either some kind of design. We want to design, let us say, a dam or a bridge, all right, for which we want to know what is the magnitude of the flood or the discharge that is expected in the river, because your design has to be safe for the worst case scenario. All right. If you make some error in the estimation of the magnitude of the discharge or the peak flow for which you are designing your hydraulic structure, then the as you can expect, as you can understand, the results can be, or the consequences can be catastrophic. All right. If you make 10%, 50%, 20% error in the estimation of the peak discharge, you cannot actually afford that. All right. So, design is one important thing, hydrological design or hydraulic design, in which the knowledge of probability or stochastic analysis is required, so that we can develop what is called a reliable design. All right. What is the other one? Well, we have many this water resources systems projects, all right, in which we need to operate the system or the water system under uncertainty. Okay. For example, flood management and drought management. You want to go through the process of this these extremes or your floods and droughts, all right, but you want to be able to forecast these variables, that is your discharge, rainfall, etc., well in advance. All right. If you can say that next month this is going to be the rainfall and you can be accurate, then you can conserve the water today, and then you can go through the drought situation in a better manner. All right. So, being able to forecast accurately, all right, is also required, in which the knowledge of statistics is essential. All right. So, these are some of the reasons. So, for the second one, I will say design and forecast under uncertainty. Okay. And there can be many other applications of stochastic analysis or stochastic hydrology. All right. We will not go into the details of all of them. All right. Okay, so with this little bit of background, what I would like to do is start defining certain basic principles and concepts which we are going to need when we do this stochastic analysis or statistical analysis. All right. Some of these concepts or definitions are very simple, you may have seen them earlier, but nonetheless they are very important and we are going to just review them quickly. Okay. So, I am going to start with the definition of what is called a random variable. What is a random variable? As the name suggests, it is some physical variable which has uncertainty involved in it, all right, which is random in nature. That is as simple as that, but that is for a layman, all right. As hydrologists, how we are going to define a random variable is that it can be defined as a variable which can assume any value and that value is within certain range, all right. Okay. The random variable can assume any value or take up any value, but that has to be within certain range described by a certain probability distribution. Okay. So, this is the definition of a random variable. What is it? It can be defined as a variable which can assume any value, all right. It can take up any value, all right. For example, let us say you have rainfall. Rainfall can take up any value tomorrow or next year depending upon the time frame between, let us say, minimum value is 0, maximum is theoretically it is infinity, but maximum can be 100 centimeters or something. So, it is a variable which is uncertain in nature and it can take up any value within the specified range, all right. But the important condition is that the value which it will take is described by a certain probability distribution. The beauty or the good factor or the advantage about defining the random variable is that the random variable assumes a value. However, it is described by a certain law, although it is random, but it follows certain probability distribution, and there are many kinds of probability distributions we will see in this chapter or in this module. Different variables will follow different hydrologic probability distributions, all right. So, this is the definition, and the mathematical representation of a random variable is like this. You have probability of your random variable x having a value less than or equal to small x is equal to small p, okay, where your x is the random variable, all right. Small x is any value. For example, if capital X is your rainfall or the annual rainfall and small x can be, let us say 100 centimeters, right. Then let me first say that your p is equal to the probability which will be described by certain distribution, and this is between 0 and 1. Okay. So, for example, if we take the case of the annual rainfall, okay, for example, let your capital X be annual rainfall. So, your random variable is annual rainfall. What is going to be the annual rainfall next year, or what is going to be the peak discharge next year? Okay. So, that will relate to what kind of drought situation may be in, what kind of flood situation may be in, all right. So, these are the kind of decisions we can take. So, if we say that x is equal to annual rainfall, and let us say x you want to define, if you are, let us say, in the if you want to analyze the drought condition, and then you are looking at, let us say, if the rainfall, annual rainfall is less than or equal to 45 centimeters, then you say we are in trouble as far as the drought is concerned. So, we can define this kind of thing or this kind of event depending upon our need, all right. So, for this case it is going to be the random variable will be or can be defined as your x less than equal to 45 is equal to some value of p, okay, and this p can be determined using some probability distribution which the annual rainfall follows in that area. It can be determined using that, for which we use the historical data. Okay. So, you take the historical data, you fit a certain probability distribution, all right. So, this is the definition of what is called the random variable. Moving on, we define what is called a sample. Okay. What is a sample? Well, it is nothing but a set of observations and let us say that this is x 1, x 2 up to x n, all right, of the random variable is called a sample. Okay. So, what is a sample? If your random variable, as I said in the previous page, is your annual rainfall, okay, then let us say your set A is the values of the annual rainfall in the past 3, 4, 5 years, 10 years, 20 years. Let us say we have 20 years of data, of rainfall data, all right. For example, here if I say that the annual rainfall for the last 5 years was 100, 120, 150, 57 and let us say 75. What is this? This is a set of observations. This is the annual rainfall observed for the last 5 years, all right. So, a sample is nothing but a collection of the data for that particular type of event or the random variable which we have defined. Okay. So, this is a sample. Most of our probabilistic analysis will be carried out on the sample, but we need to understand what we have is what is called a population. Okay. Population is a hypothetical concept, infinitely large set of a random variable. Okay. Possessing constant statistical properties. Okay. This is important, possessing constant statistical properties as far as the population is concerned. So, what is the difference between a sample and a population? Sample, we said it is just the collection of data points from your universal set, let us say, all right, 5 years of data or 10 years of data. But population is something hypothetical, the data set is extremely large, infinite, all right, but the condition is that it possesses what? Constant statistical properties, and the statistical properties we are talking about is what? Is like mean, standard deviation, skewness, those kind of things, all right. We will come to those little later in this chapter, but if you have a population, the mean of that population is always going to be constant, which is not the case for a sample. If you take a sample of 20 data points, it will have certain mean, standard deviation and so on. You take another sample of the same hydrologic variable, all right, let us say annual rainfall in the same area. You have a 20 years data here, another 20 years of data, their means and standard deviations and other statistical properties will not necessarily be the same. all right. So, sample is a very small set and population is infinitely large, all right, but the statistical properties are constant. Okay, let us move on. Then we have what is called a sample space. What is a sample space? It is a set of all possible sample, set of all possible samples that could be drawn from the population. Is called a sample space. All right. So, what is a sample space? It is a set of all possible samples that can be drawn. All right. A sample is the collection of the observations of the data. All right. So, it is a set, and sample space is what? Let us say you can draw 10 different sets or 10 different samples. All right. So, that whole space actually from which you are drawing these samples is called the sample space. Okay. Next thing is what is called an event. Okay. What is an event? Event is a subset of a sample space. All right. An event is a subset of a sample space. All right. This event is something which we can define, all right, whenever we are dealing with the hydrological variables or data. An event is something which we can define depending upon our need or the practical use. All right. This is very important to understand. All right. How? I will take up maybe one example which will demonstrate. We can define an event. For example, let us say you are analyzing the flood situation. All right. When you want to manage your flood situation, you want to define an event in such a manner that you are able to define the flood in a certain manner. For example, you have the annual peak discharge data, that is what you want to analyze, and then you say that a flood is defined in such a manner that, or an event is defined, event is equal to flood, for example. So, the event is supposed to have occurred when the peak discharge in a year is greater than or equal to a certain magnitude. Similarly, how would you like to define an event when you are dealing in a drought situation? You would say that the annual rainfall is less than this particular value. All right. If that is the case, we are into a drought situation. It can be a tiered system also. All right. For the drought case, for example, you can say event A is what? If the annual rainfall is between this and this limit, then you have moderate drought situation. If the annual rainfall is between this and this limit, then you have severe drought situation, and so on. All right. So, an event is something we can define based on our need. All right. So, for example, if your random variable is annual rainfall, then you say x is equal to annual rainfall. Okay. That is your random variable. What is its range? Well, range of x, let us say, is between 0 to some maximum value. Theoretically, it is infinity. All right, but practically it would be the maximum value which has been observed, which may be annual value of 200 centimeters or something, right, okay, or something like that. Then you may want to define an event A, all right, is such that this annual rainfall x is less than equal to 30 centimeters. Means what? What is our emphasis? We are trying to look at drought situation. Okay. Then you say let me say that this is A1. Then you want to define another event A2, all right, such that your x is greater than equal to 150 centimeters. Means what? You are dealing with the wet conditions or maybe flooding, all right. So, this x, which is the annual rainfall, you may have to do rainfall runoff modeling and determine what will be the value of the flow or the peak discharge, and then put the limits on the or define the event in terms of the peak discharge, all right. So, this way we see that we can define an event the way we want depending upon our need, all right, and then we can analyze the data, the historical data we have, and determine all kinds of probabilities, all right. For example, let us say you have, let us say 30 years of data with you, okay, for x, means annual rainfall, and your event you have defined as this one, let us say this one. How can you find the probability of the event A1 occurring? Probability of A1 is equal to what? How will you find this out? If you have 30 years of data for annual rainfall, think about it. I will give you the answer little later, all right. It is a simple concept of probability. You can just count the number of years in which the rainfall was less than 30. Okay. So, let us move on, and now we define what is called the probability. Okay. What is a probability of occurrence of an event A? So, we have defined you see the sample, the population, the sample space, the event. Now, we are defining probability of occurrence of an event, all right. That is P of A is defined as under the limits as n tends to infinity, okay, of what? N A over n, okay. Let me define these things. What is n subscript A is what? Yeah, it is number of occurrences of the event A, okay, and n is what? The total possible number of occurrences of your event A, of course, okay. So, in the previous example, let us say we had 20 years of data, all right, and out of those 20 years of data, in 4 of them the annual rainfall was less than 30 centimeters, okay. So, what will be the probability of event A occurring? That is, what is the probability that the annual rainfall is going to be less than or equal to 30, all right. So, it will be nothing but 4 divided by 20, okay, or it is 1 over 5, right. So, you can get that using your data very easily, okay. So, you see that we can analyze our historical data, and then we can define the event based on our needs, and then we can find out various probabilities by looking at the data. Now, a simple definition of probability will give you this kind of information which we have just looked at. However, there may be many events which may be interacting with each other. For example, you may have to define an event A, event B, event C, and then event A, B, C may be interacting with each other, or they may be independent. You may want to find out the relationship between those events, all right. That is, for that we need many different types of analysis, and there are what are called laws of probabilities, all right. I am sure you may have seen these laws of probability, but we will look at some of these, okay. So, the next thing we are going to do is what is called the laws of probability. Okay. There are many of them, and the first one which we will look at is called the law of total probability. law of total probability. Let us say that the space, the total space, you can divide into m different events, or you can draw m different events, and let us say these are A1, A2, A3 all the way to Am. Okay. So, let us say you have a sample space in which you can draw m number of samples or m number of events can be defined. All right. Then the law of total probability states that the sum of the probabilities of all these events, all right, A1, A2, A3 is equal to what? Will be equal to 1. All right. That is all. So, mathematically what we can say is that probability of the event A1 occurring plus probability of the event A2 occurring plus probability of the event A3 occurring, and so on all the way to what? Plus probability of your event Am occurring should be equal to what? Probability of your total sample space occurring, that has to be equal to 1.0, right. For example, in your earlier case, let me go back up here, you had 20 years of data, right, total. 4 years you said what was the event A? Event A was your annual rainfall was less than equal to 20, right. So, if you could say that your event B was your rainfall value was more than 20, if that was your event B, then how many years are there? 16 years of data. All right. If the 4 years of data had rainfall value less than 20, the remaining had to have a rainfall value more than 20, right. So, that the total sample space, which is your 20, could be divided into how many? 2. So, m value is here 2. So, you see that your P1, P of your A plus P of your B has to be equal to what? Has to be equal to 1, right, as per the law of probability, right. Now, we have seen that P of A is what? 1 by 5 or 4 by 20, all right. So, if your this is 4 by 20 plus P of your B is equal to 1. So, that will give you P of your B is equal to 1.0 minus 4 by 20, or you could say that it will be 16 by 20, all right. You would have known that already. So, you could verify either the law of total probability, or knowing the law of probability, total law of probability is true, you can find out something that is unknown, all right. So, that is where some of these laws are useful to us. Okay. Number 2 is what is called the non-event or law of complementary or complementary law or complementary probability. Okay. As it is clear, if A is your event A occurring, all right, and if you define another event A bar as event A not occurring, okay, then your probability of complementary event, which is A bar, is given as what? 1 minus of your P A. Okay. This is what is called your law of non-event or complementary law, whatever we call it, or law of complementarity. All right. So, you have an event A occurring. If you can find out the probability of an event A occurring, you always know what is the probability of that event not occurring. For example, flood. If you can say that the probability of occurrence of flood next year is 0.5, what is the probability of non occurrence of the flood? 1 minus 0.5, that is also 50%. All right. Another example is we just looked at, if you come here in the pink, this is also you can find out by as non occurrence, all right, because occurrence of an event was annual rainfall value being less than equal to 20, and the non occurrence is what? Greater than 20, all right. So, it is the similar thing. Okay, now the third one we are going to look at is what is called the conditional probability, or the law of what is called conditional probability. As the name suggests, when do we need to use the conditional probability? Well, when there is a condition about another event which has already occurred or not occurred, or something like that. Okay. So, conditional probabilities are useful when you are dealing with more than one event, all right, such that one event will depend on the other. So, that we are defining a conditional probability of occurrence of an event given another event has occurred. Okay. So, let me first define it and then we will maybe discuss about the physical nature of this. Okay. So, this is denoted as P, or the probability of event B given A. What is the conditional probability? Probability of an event B occurring given A has occurred, all right, is equal to what? As per the law of this conditional probability, it is given as the probability of A intersection B divided by the probability of A. Okay. This is what is called the law of conditional probability, all right. Now, this involves something which we have not discussed. What is this P, or probability of A intersection B? Okay. This we are going to define next, which is for your union and intersections. Okay. So, what are the unions and intersection? We will look at this concept. Let me first give you the relationship about this. So, if you have events A and B, see, if you look here in the conditional probability, you see this thing in the numerator, we have A intersection B. So, you have two events A and B, and we want to find out their unions and intersections. Okay. So, the union is defined as A union B is what? As per the laws of this unions and intersection, it is defined as probability of A plus probability of B minus your probability of A intersection B. Okay. I am sure you know all these concepts. You may have seen in your earlier classes set theory and unions and intersections, but let me quickly give you this. Let us say this is your overall sample space in which you have two events. This is A and this is B, all right. So, what is the A union B, all right. So, you have an event A occurring, you have an event B occurring. When can you say that both the events A and B are occurring, and when can you say either A or B is occurring, all right. So, depending upon that we define A union B and A intersection B, right. So, this is A union B means this whole thing. So, this whole area is how you define as the A union B, and which probability is given by this. Okay. How about A intersection B? Intersection is basically AND, okay, in which things are common to both the events, right. So, this is your, let us say this was your A and this is your B, all right. So, what it is your A intersection B and this is your A union B. Okay. So, when you have these two events, the two events are related with an OR operator. Okay. So, when you say A union B, you are saying the probability of occurrence of this or that, right, event A or event B, okay, that is A union B. And when you say intersection, what you are saying is that it is the space is common to both the events A and B, right. So, the two events are connected with an AND operator. Okay. So, when we are dealing with the mathematical operators. Okay. So, coming back here, what is your A union B is given by this equation, all right, in which then this appears. How do we define an intersection mathematically? Knowing the probabilities of the individual events, this is defined like this, is equal to probability of event A multiplied by the probability of event B when or if A and B are independent. Okay. So, when the two events A and B or the occurrence of event A does not depend on the occurrence of event B, then your A intersection B is given by the product of the individual probabilities, all right, P A times P B. Okay. That is what we are saying, and this is equal to your P of your A multiplied by what? P of your B given A, that is your conditional probability if not. Okay. You see that your this equation, the second one is same as the law of your conditional probability. You see this, P B given A is P A intersection B divided by P of A, right. It is the same equation we have written there. So, P A intersection B is equal to what? It is P A multiplied by P of your B given A, if they are dependent on each other, or if the occurrence will depend on the other one. Okay. However, if they are independent, then you just say A intersection B is just the multiplication of the two probabilities, all right. What about if they are mutually exclusive? If they are mutually exclusive means what? They are just separate, all right, means you have this space, they are separate, completely separate, they have nothing common. So, when you have two events in which there is nothing common, they are called mutually exclusive. So, A intersection B is going to be equal to what? A intersection B is actually defining the common space, and the common space here is what? 0. Okay. So, it is going to be your 0, all right. So, this way we see that there are basic laws of probability we have seen, the total law, the conditional, and the intersections and unions, which are quite useful in analyzing certain situations in which we have more than one event and there are interrelationships between them. Okay. So, from here we will move on and then look at the data representation and data analysis, and then we will start defining certain basic concepts and when we start analyzing our hydrological data. Okay. What do you do with your data first thing when you are given in your statistics chapter in your earlier classes? The first thing we do is what is called the frequency histogram, or we analyze the data in terms of frequency of occurrence for each class or for each magnitude, all right. So, the next thing we are going to look at is what is called frequency histogram. Okay. What is done in this is you have the data. Let us say that we have data set x1, x2, x3 all the way to some xn. Okay. What we do is we divide the data into classes. Okay. Let us say you have the rainfall, annual rainfall, minimum value is 0 or maybe 10 centimeters, maximum is let us say 200 centimeters. So, this is the range. This range we can divide into different classes, that is 10 to 30, 30 to 50, 50 to 70 and so on, all right. So, these are called different classes. So, first thing we do is we divide the data into different classes, right. Then what do you do? Then you count the number of occurrences or observations, right. Remember this, falling in each class. Okay. So, what you do is you have the data, you have taken the minimum and the maximum, you have divided that range into different classes, and then you manually just scan through the data and put them in different classes, all right. So, that you will have the number of occurrences of your event or observations in each class, all right. And then what you do is you just plot the number of occurrences, all right, which is called frequency actually, against the classes. Okay. So, it will look like this. So, this is your classes, which will actually represent the magnitude of your random variable, and this is your frequency, or it could be in terms of number of events or occurrences in that class, all right. So, you would see that this is normally done in the form of a bar chart. I am sure you have done this in your earlier classes, all right. Your each bar represents what? Either the number or the frequency or a fraction, all right. How do we define the frequency or the fraction? It is basically the number of occurrences divided by the total number of occurrences. So, either you can plot this number n a as the length of this bar, or you can plot this whole thing, the fraction n a over n. Okay. So, it depends how you are representing your frequency histogram, all right. So, this is very simple, it is basically a simple data analysis in which we get an idea of which class is occurring most frequently, what is the average value, all right. We get a lot of good information once we just plot this data or this frequency histogram. Okay. Okay, let us move on. The next thing we will define is what is called the relative frequency function. Okay. This is f s of your x I, okay, where the f s of your x I is defined as what? It is n I over n, okay, as I said earlier already, where n I is what? N I is the number of observations in ith interval or ith class, okay. N is the total number of observations in your data set, that is, and this S actually denotes what? That these observations are from a sample. Okay. After all, we are working with the sample only, okay, and then we can plot this. So, it is basically nothing but this one here. Okay. So, if you are plotting n a over n or n I over n, it is called the relative frequency function, but if you are plotting n a or the number of occurrences, it is called the frequency histogram. So, there is a minute difference here. Okay. In fact, this the ordinate of your relative frequency function, all right, which you have just defined, represents what? It basically represents the probability of occurrence. Okay. Do you see that? We had already defined this ratio, which is Ni over n. What is this? Under the limits when your sample size is too large, this is the probability of occurrence of that event A. What is that event A? It is the class I. All right. So, we say that the probability of occurrence of your random variable such that its value is between the lower class limit to the upper class limit, okay, that class value, all right, minimum and maximum of that class or the ith class is equal to what? Is Ni over n. Okay. So, this is actually then nothing but mathematically we can define it as what? It is the probability of your random variable having a value what? Between certain range. And what is that range? The upper limit is, let us say x I, and if the interval, the class interval is delta x, the lower limit is going to be x I minus delta x. Do you see that? What is this probability? This expression is saying what? This expression is saying that the probability of occurrence of your random variable x between this and this range, which and which? The lower limit this and the higher limit this is given by this guy here or this fraction. Okay. So, this relative frequency function actually gives you the information about the probability of occurrence of your random variable within a certain range, which is a very useful and important information. Okay. So, the class intervals can be defined in a manner which is useful for our water resources management. Okay. All right. So, related to this relative frequency function, we will define another term which is called cumulative frequency function. Okay. And let us say this is CFF, and this we denote as capital F subscript s of your xi. Okay. As the name suggests, it is what? It is the cumulative type of function. What is a cumulative function? Which is accumulated. All right. If you integrate another function, in this case that another function is your RFF or the relative frequency function. All right. So, the cumulative frequency function is nothing but the cumulative of your relative frequency function. Okay. So, if you define it, it is nothing but is the sum of the relative frequency function. I am not going to write it, I will use this abbreviation up to a given point, any given point or any given magnitude of your random variable. Okay. So, how is this then defined? Your Fs of your xi is equal to the summation of your Fs of your xj. So, we are using another index here such that your j varies from where to where? From 1 to I. You see that the index here is I. All right. So, it is defined up to that point. That point is the ith class. All right. Up to that, what is it? It is the summation of everything before it. All right. So, again this will represent what? This will represent the probability of what? Of your random variable x having a value less than or equal to xi. Okay. So, what you are saying is that the relative frequency function gives you the probability of occurrence of the random variable within a certain range. However, the cumulative frequency function or CFF is the accumulative value of your RFF up to that point. That is to say, it will give you what? The probability of occurrence of your random variable before that, okay, just earlier. That is why we are having p x less than equal to xi, that particular value. Okay. All right. So, let us continue and then we define what is called the probability density function. This is a term which will be encountered very frequently. Okay. PDF or it is simply written as f of x. It is like any function. Well, what is it? The relative frequency function which we have just seen is defined for a sample. Okay. The relative frequency function was defined for a sample. What is a PDF? The corresponding function for the population. Function for population. What is a population? A sample of size infinite or infinity as n tends to infinity and delta x tends to 0. Okay. So, we are putting two conditions. What are those two conditions? First one is that the sample size becomes infinity or you have a very large sample, all right. Also the delta x tends to 0. So, that you are talking about from discrete to continuous, all right. So, delta x is extremely small. Under those conditions, that RFF is defined as the PDF. Okay. Mathematically, we say your f of x or the probability density function is nothing but under the limits as n tends to infinity and delta x tends to 0 of what? Your fs xi or x divided by delta x. We are dividing by delta x and we are taking the limits, all right. So, this is the definition of your PDF. Okay. So, essentially what we are saying is that the RFF is for your sample and the PDF is for the population. Okay. Similar to that, we will define what is called a cumulative distribution function. What is a cumulative distribution function? It is denoted as capital F x, all right. The CDF is defined for corresponding population. It is similar concept actually. Okay, let me first say that your cumulative frequency function is defined for a sample, right. I should have said that earlier, and then the CDF or the cumulative distribution function is defined for a population, all right, or it is the corresponding function which is defined for a population as same thing n tends to infinity and delta x tends to 0. Okay. So, mathematically what we are going to say is that your capital F of x is equal to what? Is equal to the function under the limits of what as n tends to infinity and delta x tends to 0 of your f s of your x. Okay. All right. So, we have seen that there are two functions, one is the PDF, other is the CDF. All right. It should be very clear that one is the cumulative of the other. All right. So, if you have PDF with you, you can always find the CDF by integrating that. On the other hand, if you have the CDF, the cumulative function, you can differentiate that, all right, to get the PDF. All right. So, what is the relationship between the two? Well, let me go to the next page and say that your PDF is nothing but the derivative of your CDF with respect to x. Okay. And also, what does this represent? This represents your x less than equal to x. What is this probability of random variable having a value less than equal to a particular value? This is given by your CDF, okay, which is given by minus infinity to x of your FU du. Okay. So, this is a very important result, all right, which will through which we can find out the probabilities of different kinds, all right. So, I am afraid I am running out of time today. I will come back and revisit some of these relations more closely. Okay. So, basically what we have seen today is we have started the probability chapter. We have looked at some basic concepts, what is how the probability is defined, why the statistical analysis is needed, and then different laws of probability, and then towards the end we define the concepts of relative frequency function, cumulative function, and PDF and CDF. Right. So, I would like to stop here today, and then we will pick it up from here tomorrow. Thank you.